In econometrics, we are going to deal with more than one variable at the same time. Actually, that is the main point. You want to see the effect of one variable such as education on another variable such as income per capita. The whole point would be to see how a group of variables affects another group of variables. Therefore, we are going to need to study how to model multiple variable interactions. So far, we only studied the distribution of one variable at a time. In these notes, we're going to start studying the distribution of more than one variable at a time. We're going to start with an example. Consider a three-sided die. And yes, three-sided dice exist. You can buy them in Amazon. You can see them in this picture here. We are actually going to model two experiments at the same time. The first will be flipping a coin, and the second will be rolling a three-sided die. Let's review the two experiments separately. The experiment of flipping a coin was modeled in notes 1. So we had the sample space equals HT. So there are basically two possible outcomes. You can flip a coin and get heads or tails. But then, for our purposes, it is useful to recode the possible outcomes to a random variable. How do we recode it? Well, there are many ways to do it. The most useful way is the following. If I flip a coin and I get heads, I'm gonna define my random variable x, and the value would be x1 equals 0. And the outcome tail, I'm gonna recode to x equals 1. Now keep in mind that the probability of x equals 0, for instance, is going to be the same as the probability of the outcome that was recoded to 0. So basically the probability here would be half, because the probability of flipping a coin and obtaining heads was half. Now, consider the experiment of a three-sided die. It's very easy to define the random variable because the outcomes are already numerical. So here we have the possible outcomes, 1, 2, 3. I'm going to define the random variable. I'm going to call it y. The values are 1, 2, 3. It's very easy to recode. And I'm going to model this die as perfectly balanced. Therefore, the probabilities are 1/3, 1/3, 1/3. Note that to differentiate the density functions, we are using two notations now, fx and fy, where x and I are in the subscripts. Okay, so how am I going to model both experiments at the same time? Well, consider first the list of all possible outcomes. It is given here. How can I come up with a way to make sure that I listed all possible outcomes? Because that's my first step. I like setting up a 3 in the following way. The first experiment has two possible outcomes, H and T. Now, for H, I can get 3 possible outcomes of the die. 1, 2, and 3. And then for T, I can get 3 possible outcomes of the die as well, 1, 2, 3. So for each node, starting with the first experiment, get all the possible outcomes, and then from each node here to the second experiment, get all the possible outcomes. If there were a third experiment from each node, you have all possible outcomes and so on. That way you can make sure you didn't forget anything. Thus, the first possibility is H1, and that is here. Then H2, and that is here, and so on. Okay, notice that when I have H and 1, my random variable x is 0, my random variable y is 1. Why? Because from here, when the die rolls and the outcome is 1, I recoded my y to 1. And when I flipped the coin and I got heads, I recoded my variable to 0. So here are the variables of my random variables. Now, Notice that there are 6 possible outcomes, and intuitively, they are all equiprobable. There is no reason to believe that one of the 6 outcomes is more likely than the other, because, at least in theory, the coin is completely balanced and so is the die. So I am going to assume that all outcomes have the same probabilities. So the probability of each outcome is going to be 1/6 each. It has to be 1/6 if the events are equiprobable, because there are 6 possible outcomes and the probabilities have to add up to 1. So in this way, 1/6 times 6 equals to 1. Okay. With that in mind, let's define a joint distribution. The purpose is to ask questions such as, what's the probability that x equals 0 and y equal 1? Which we already modeled above, equals to 1/6. But now how do we denote that? We denote that in the following way. Probability x equals 0, comma, y equals 1. This comma here, in this context, means and. Okay, I want both statements to be true, x equals 0 and y equal 1. On the other hand, another way to denote the same thing is the following, f of xi ly. So when I denote it like that, I call it the joint density function. And what I mean is, I want my x to be whatever number I have here, and I want my y to be whatever number I have here. So this comma here also means and. Now you can see from table 3 that this probability equals 1/6, because that's the way we chose to model it. Because stating the joint distribution is how I define a model, usually in the exercise I have to tell you what the joint distribution is. But often you have to look at the joint distribution and derive from that the marginal distribution. And by the marginal distribution, I mean the individual distributions of the variables. For instance, let's say all the information I gave you is this, the joint distribution. Okay? How would you define the marginal distributions? How would you go from this table to this table? Or to this table? How do you go from the big table to the small table? Well, here's the formula. Given the joint distribution of two variables x and y, the marginal distribution of fx of xy is the summation across y where xi is fixed and y is varying. Okay, that sounds complicated, but it's actually really easy. What do you have here? Let's say, for example, I want the probability of x equals 0. Okay, so what I'm looking for is fx of 0. How would I do that? Well, notice that there are 3 possibilities where x can be 0. When y equals 1, when y equals 2, when y equals 3. So what I do is I add these probabilities here. Okay? So I am adding for different y's, but keeping my x fixed equals to 0. And that is what this notation means. I am adding for different y's, keeping my xi fixed, whatever is here. So in my example, my xy equals 0. So I'm going to keep 0 fixed, but keep adding the i's. So what we have here is f of 0, 1. That's the first term of the summation. F of 0, 2. That's the second term of the summation. F of 0, 3. That's the third sum of the summation. Fix x, adding across I. Okay, but as we saw, that's equal to, because of the information that I gave you in the beginning of the exercise, Remember, the information I gave you is this table here. But 1/6 plus 1/6 plus 1/6 is 3/6, which is equals to half. Okay? Meaning the probability that x equals 0 is half, which I already knew. The probability that I throw a coin and I get heads, we already had modeled as equals to half. So in summary, when you are given the joint distribution, meaning you are given this information here, but you want to go from the joint distribution to the marginal distribution, meaning you want to figure out fx or fy. If you want to figure out fx, you fix an x and sum for y. If you want to figure out fy, you fix a y and sum over the x.